Partial exam 2013-2014, problem 1. Here it's a simple application to Gauss's law to find the electric field, and also we have to find the electric potential V. First of all, we have a uniform charged object, spherical object. It's not metallic inside with radius A. We have a metallic shell, spherical metallic shell with inner radius B and outer radius C. And here, by using Gauss's law, I have to find the electric field at the point A, B, C, D, and after we have to find the electric potential at these points. I told you the system is in electrostatic equilibrium. Let me explain before the problem. Initially, we have the center of the system here with a radius equals to A. This sphere is non-metallic. It means if we have plus 2q, this charge will be distributed at any point inside the sphere with a volume charge density rho. We have the shell with inner radius B and outer radius C. Okay, let's say we have B and C. Here, if we don't have sphere inside, this minus 2q, you know, we have minus 3q, the charge of the shell. Without q inside, this minus 3q will be distributed at the outer surface of the shell. But because we have a sphere inside, you will get a new distribution of charge inside the shell. So we can say because the presence of a charge inside the shell, we get a new Okay, what is the new distribution of the charge inside? You know, here we have plus 2q will attract to the inner surface of the shell minus 2q. The total is minus 3q. Here we have minus 2q. So at the outer surface, we have minus q to get totally minus 3q. This is the total charge. And we can say we have this new distribution at the equilibrium at electrostatic equilibrium. We have minus q at the outer surface and minus 2q at the inner surface. Okay. So part 1, I have to find the electric field by using Gauss's law outside the system, let's say at this point. Second point will be inside the shell at this point. Third point is between the sphere and the shell, and this point is inside the sphere. Okay, we have to find for each point. Here we have point A, point B, point C, and point D by using Gauss's law. You know, at the point, first of all, outside the shell, we have the position R must be greater than the outer radius C. At the point B, B is between B and C, between the inner and the outer radius. So the second point R is between C and B. The second zone here at the point C, C is between A and B, at this point between A and B. And last we have the point C is between 0 and A. I have to find the electric field at any point in these regions. First of all, let's start with the first one, this one. You know, as we have a spherical object, to use Gauss's law, we have to say we select a sphere of radius r as Gaussian surface. And you have to put the conditions. First of all, you know, E must be parallel to dA. Second point, E must be radial. Third point, E must be constant at any point on the surface. And in general, phi equals to integral of E dot dA equals to Qn divided by epsilon. This is a general case. It's important to write this information before starting the calculation. As you see, we have a, this one is Gauss's or Gaussian surface. And you know, we must have dA must be perpendicular to this surface at any point. This one is dA. You know, the outer surface of the shell is negatively charged. So here we have negative. In this case, E must be inward the system at this point. So E and dA are opposite. Flux equals to E dot dA cosine pi equals to Qn. Inside we have minus the total charge inside minus 3Q plus 2Q divided by epsilon. You know, E is constant, integral of dA equals to A. So here we get minus EA equals to minus Q divided by epsilon. You know, this term concerns only the Gaussian surface. The area of this spherical surface equal to 4 pi r square. R is the distance between the center to this point. It's the radius of the Gaussian surface. So we can say plus and plus, we get E equals to Q divided by A equals to 4 pi r squared times epsilon. We can say 4 pi epsilon 0 times r squared. This is the value in the region between C and infinity. Okay, we can say between C and infinity. The second case, if R is between C and B, let's say at the point B. Okay, also we use Gaussian surface, this one, and in general, inside a conducting material, we don't have a field. Flux equals to integral of E dot dA equals to Qn. Inside this one, inside we have minus 2Q plus 2Q. So minus 2Q plus 2Q divided by epsilon equals to O. So E equals to O in this region. We can write here for R between C and B, E equals to O. Okay. Now let's take the field as a point C. For R at the point C, I mean the distance is between A and B. Okay, here you have the distance between A and B in this region here. At this point we have a positive, here we have a positive charge and here we have a negative charge. So the field will be from the positive to the negative. So it must be out, this E. And about dA, dA is perpendicular to the surface. So we have the same direction of E and dA. We can say phi equals to E dA, E times dA cosine 0 equals to Qn. Qn inside the Gaussian, this one is Gaussian surface. Inside we have only 2Q. E is constant, so EA equals to 2Q over epsilon. A is the area of Gaussian surface, which is at a distance or radius equals to R. So A equals to 4 pi R square. E equals to 2Q divided by 4 pi epsilon R square. This is the answer. At this point C, if you look inside here, you have a spherical object. You can consider this charge as a point charge. Okay, the second method. Here you can say we can consider the sphere as a point charge at the center O. So we can say E at the point C equals to K times the total charge here equals to 2Q divided by R square. We get the same result. K equals to 4 pi epsilon 0. Okay, the same result. Okay, so this case is the case 1, 2. If R is between A and B, we have E equals to 2Q divided by 4 pi epsilon 0 R square. The last point, point D, here we have a Gaussian surface, the black one. At the point D, we have dA is out, and you know we have a positive charge uh, of the sphere, so E is out. E and dA have the same direction, E and dA. So we can calculate phi equals to integral of EDA equals to Qn divided by epsilon. The angle between them equals to O, so we have E dot dA cosine 0 equals to 1, okay? Equals to Qn epsilon 0. Qn is inside the Gaussian surface here. You know, here we have a uniform charge distribution. It's not metallic. And I give you, we have a volume charge distribution rho. So Qn inside equals to rho times Vn. And Vn, you know, this one has a radius equals to r. So equals to 4 over 3 pi r cube. Okay. E is constant. We put E outside times A equals to rho 4 over 3 pi r cube divided by epsilon, and A equals to 4 pi r square. A is the area of the Gaussian surface equals to 4 pi r square. We get finally E equals to rho 4 over 3 pi r cube epsilon times A. Okay, equals to okay, here you see E is not is independent to Q. I need to enter Q inside the relation. How? By using rho. You know, we said here Qn equals to rho Vn. Also, we can say Q total. You know, Q total of this sphere equals to 2Q. 2Q equals to rho times V total. This sphere has a radius equals to A. So 2Q equals to rho times 4 over 3 pi a cube. So rho equals to, we have 2 and 2, okay, equals to 3 times 2 times q divided by 4 pi a cube is equal to 3 over 2 q. We have epsilon. No, pi a cube. Okay, we substitute the value of rho here. We get finally equals to 3 over 2 q divided by pi a cube, and here we have 4 pi r cube, and down we have 3 epsilon 4 pi r square. Okay, this one is rho. We get finally, we can eliminate 3 and 3. We have 1 over 2 pi, no, this pi and this pi, this 4 and this 4, r cube with r square, we get r. So we have q divided by 2 pi epsilon 0 2 pi epsilon 0 a cube. Excuse me, r is up, is here. This is the final answer of E. In the case where r is between 0 and a, okay, we have E equals to q r divided by 2 pi epsilon 0 a cube. Okay. Part B, I want to find V at each point. Let's go to solve it. Part B, I want to calculate the electric potential at A, B, C, D. Okay. Here, you know, we have a relation between the electric field and the electric potential. E, in general, equals to minus gradient V, okay? Or equals to minus dV divided by dr. So dV, we can write here dV equals to minus E dot dr. We have to understand very well the meaning of each term. dV is the difference between 2 points, is the difference of potential between 2 points. If I want to calculate the potential at the point A, for example, I want at the point A, To calculate the potential at the point A, we have to take a difference of potential between A and another point. Let's take the infinity. Why? Because I know at infinity we don't have a potential. So it's a known value. V infinity equals to O. So it's easy to calculate V at A. If we do the integration of this one and this one, and V will be between infinity and the point A. And here R, you know R is the distance from the center to the point. Okay, it will be from infinity to the point A. Or you can say from the point A to infinity. Nothing will change. Okay, let's take the point from infinity to the point A. It means I have a displacement from here to here, so dr must be in this direction. We move from infinity to RA. You know, here at the outer shell, we have a negative charge. In this case, E must be in toward the system in this direction. This is E. The angle between E and dr equal to 0. So we can write minus E dr. Okay? And you know, in the case of R greater than C, E equals to Q divided by 4 pi epsilon 0 R square. We can substitute the value of E directly here. We get Q divided by 4 pi epsilon 0 R square dr, and the limit is between infinity and RA. Okay, let's calculate the integral. Integral equals to VA minus V infinity equals to minus. Q is constant, 4 pi epsilon 0, and here we have the integral of R square. Here we can put it R minus 2 times dr. V infinity equals to O, so VA equals to minus Q 4 pi epsilon 0. The integral here equals to R minus 2 plus 1 divided by minus 2 plus 1. And the limit is between infinity and RA. Okay, you know minus 2 plus 1 equals minus 1. Minus times minus equals to plus. Q divided by 4 pi epsilon 0. R minus 2 plus 1 equals to R minus 1. We can put it down. So equals to 1 over R A minus 1 to infinity. Okay, we can write here the value in the case of R is greater than, let's take greater than or equal to C. We have V equals to Q divided by 4 pi epsilon 0 times R at any point outside the shell. Okay, now we calculated the potential at these points. Here we have the point A. You know, I take the limit between C, R is greater than C. So it means from this point, at the point C, the distance from here to here equals to C, and outside. Let's take this point as A prime. We can calculate VA prime by using this relation. We can say directly VA prime equals to Q divided by 4 pi epsilon 0 RA prime. RA prime equals to C. So we can say C. Now, second point, I want to calculate the potential inside the shell. Let's say we have point B. Okay? You know, in the case of a metallic object, for example, I give an example here. Here we have a metallic object. Inside, we don't have a field. E equals to O. But we have E equals to minus dV divided by dr. So as E equals to O, in this case, V must be constant. You know that derivative of the constant value equals to 0. V is constant. So V inside the conducting object equals to constant at any point. We can say at here, this point 1, at the point 2, at the point 3. V1 equals to V2 equals to V3. We come back to this problem. Here we have inside the object, we have VB. So in this case, VB equals to VA prime equals to, let's say here we have VB prime. Okay, like this one. So we calculated VA prime. So here we can say VB equals to VB prime equals to VA prime, and VA prime is calculated before here equals to Q divided by 4 pi epsilon 0 C. So that it's important here to calculate the calculation before to find VA prime, and inside the shell we have a constant potential. So VA prime equals the potential of any point on the shell. So here we can write in the case of R is inside it means R is between B and C, and V, we can say VB equals to VB prime equals to VA prime. Okay. Now let's go to the point, to the region between A and B. Between the point A and the point B. Let's take point C. At the point C, dV equals to minus E dot dr. I take the displacement of the 2 points. You know, we have C. I take C and B prime. Okay, we can put another point here. I study R between C and B. No, excuse me. R is, I take R between A and B. At A, let's take a point C prime. At B we have point B prime, and here we have a point C. We have to choose two limits for the integral. Let's take between B prime and C, because I know already the value of VB prime. You know, here we have a positive charge. E is out at the point C. And I take the displacement dr between the point B prime to the point C. So here we have dr, and here we have E, they are opposite. So the angle between, and the limit here between r of B prime and r of C, okay, equals to minus integral. You know, r B prime equals to B, equals to B. We can put B, R, C. E in this region we calculated already between A and B equals to Q divided by 2 pi epsilon 0 r square times dr. The angle between dr and E equals to pi. So we have to write cosine pi. Okay. VC minus VB prime equals to cosine pi equals to minus 1 times minus 1 equals to plus. Inside, we can take out Q and 2 pi epsilon 0, and inside we have r power minus 2 times dr. Okay. Finally, VC equals to Q divided by 2 pi epsilon 0, r minus 2, and the integral equals to r minus 2 plus 1 divided by minus 2 plus 1. Okay. And the limit is between B and RC plus VB prime. VB prime is calculated here, equals to Q divided by 4 pi epsilon 0 C. VC equals to Q 2 pi epsilon 0 minus 2 plus 1 equals to minus 1. R minus 2 plus 1 equals to R minus 1 equals to 1 over R. So here we get minus 1 over RC minus 1 over B. Okay, plus Q divided by 4 pi epsilon 0 C. We take a common factor equals to Q divided by 2 pi epsilon 0. Inside, we have 1 over B minus 1 over RC plus 1 divided by 2C. So finally, we have V between A and B equals to Q 2 pi epsilon 1 over b 1 over r 1 over 2c. Okay, here I want to add a point. The limit here is between the point C prime and the point B prime. We can use this relation to calculate VC prime. So you know R of C prime equals to A, okay? Equals to A. We can put here A in the place of R. So V C prime equals to Q divided by 2 pi epsilon 0 1 over B minus 1 over A plus 1 over 2C. Okay. This is about the point C and C prime and B prime. Now, let's take a point inside the sphere. Now, I want the region less than or equals to A and greater than 0. Why greater than 0? Because at the origin, okay, let's calculate the value and we discuss later. Here, I can take point D. dV equals to minus E dr. The limit, I take 2 points. I can take C prime and D. I have already V C prime. So between C prime and D. And here the limit of R between, I go from C prime to the point D. This is the direction of dr. And you know we have a positive charge, so E must be out. This one is E, and this one is dr. They are opposite direction. Here equals to minus E dot dr dot cosine pi. And with the limit, you know, C prime, when I say C prime, R C prime is located at a distance A. So the limit will be between A and RD. VD minus VC prime equals to, you know, cosine pi equals to minus 1 times minus 1 equal plus 1. Integral between A and RD. E in this region between 0 and A equals to QR divided by 2 pi epsilon 0 A cube, okay, times dr. Now we can calculate VD equals to Q is constant, 2 pi epsilon 0 times A cube. And inside we have the integral of, you know, we have integral of R dr, which is equal to R square divided by 2, and the limit between A and RD, plus VC prime, you can use from this result, equals to Q divided by 2 pi epsilon 0 1 over B minus 1 over A plus 1 over 2C. Okay. Let's calculate this before. It's equal to Q divided by 2 pi epsilon 0 A cube. 2 times 2, we can put it here. Oops. Anyway, equals to 4. R square, we can write R D square minus A square. Okay, plus this value. Okay, equals to, I take a common factor, equals to Q divided by 2 pi epsilon 0. Here we have, excuse me, we have A cube. A cube. No, I take only this. Q over 2 pi epsilon 0. Inside, we have R D square divided by 2 A cube. Okay? Because you have A cube here. If you want, we can put here A cube and here A cube. Okay? And we can delete this one. Okay. R D square divided by, we have 2 because 2 times 2 equals to 4. Minus 1 divided by A. Plus Q 2 pi epsilon, we have 1 over B minus 1 over A plus 1 over 9 2C. You see here we can add this term with this term. We have 2 here, okay? I forgot. 2, because we have 4, in this case we have 4 pi epsilon 0 A cube minus 4 pi epsilon 0 A cube and A2, voila. It's like this. You know, we write the final answer. We can say VD equals to Q divided by 2 pi epsilon 0 R. In general, we can say V at any point in this region. Okay, so equals to R square divided by 2A cube. We have minus 1 over 2A and minus 1 over A. It means half minus 1 equals minus half minus 1 equals to minus 3 over 2. Okay, plus 1 over B plus 1 over 9 2C. This is the answer in the case if R is between A and 0. Okay. In this case, if I ask you to calculate here, we can calculate this relation, for example, to find VC prime. Because in this case, we calculate VC prime from this relation. And also, we can use the same relation here to find VC prime. Look, because at A we have C prime, and you have C prime is located at a distance A. So R C prime equals to A. If we put here V of C prime, we have to substitute here in the place of R, we have to put A. We can see if we get the same result. Okay, so equals to Q divided by 2 pi epsilon 0. 2 equals to 1 over 2a minus 3 over 2a plus 1 over b plus 1 over 2c. Okay, so we have 1 over 2a minus 3 over 2a equals to 1 minus 3 equals to minus 2. So equals to minus 1 over a. So we get VC prime equals to Q over 2 pi epsilon 0 minus 1 over a plus 1 over b plus 1 over 2c. Look, we get the same result here. Q 2 pi epsilon 1 over b minus 1 over a plus, okay. As you see, we can calculate VC prime, which is at this point, by using the equation of the electric potential from this region or from this region. You get the same result. Okay, that's all about this problem.